Anybody that has a question for Kelsey while we're
Down in front.
getting seated up here? Be great.
Okay, I have questions for a couple of them, but I'll start with Kelsey. So you really left me wondering a couple of things. The first one is, what does Shire stand for? I love the name.
Scientific hybrid reality environments.
Okay, okay, that's good. Okay, now the other one was, could you just say what that XRF to XRD solution was again? It went by so fast, I didn't quite catch it.
Yeah, so basically the idea is that the XRF instrument in particular only takes about a couple minutes operationally. So it's a 60-second integration time plus whatever time you need to note down or take pictures and take contextual information. So that's about a 2 to 3 minute operational hit. The XRD, however, can be up to about 3 hours of integration time. So anytime you press that button, you've lost 3 hours of that instrument. So what the crew was actually doing was taking a few XRF measurements and then saying, okay, well, we might have taken 8 XRF measurements. We only need 1 or 2 XRDs, but we're using one instrument to high grade for the next.
I got a question for you, Kelsey. Is this on?
Push.
Oh, I got a question for you. Okay, I got a question for you. Is there any field instrument that you feel is less robust than others in terms of environmental conditions, temperature variations and so forth? It just doesn't work if it's too hot or something.
Yeah, is there any, I'm not sure if his mic's on, but is there any instrument that's more or less robust than others? Yeah, mine's on. I think right now what we're using for RISE, and I should have mentioned this, is commercially available instruments, right? We're testing with instruments that we've purchased from companies, and in the XRF's case, it was developed for industry and mining. So it wasn't meant to be a robust scientific instrument. So what we're dealing with now across the board with field portable instruments is those that, we didn't really have any input into the design of those instruments. So what we want to do with RISE is take these instruments and make them more robust and more relevant for scientific application. So I think, we're turning those limitations and disadvantages of the commercially available instruments into a strength in that we're able to understand the strengths and weaknesses to develop new hardware and software packages that are more relevant for geologic exploration. So any limitations I think we have are actually a lesson learned in this case. Tim?
Yeah, just building off what you said, Kelsey, I know talking to Deanne Rogers, who ran the hyperspectral instrument, I know on your field campaign, it was like super hot the first day, the instrument failed, but the 2 company representatives were out there with the team, and that they found that operational experience really useful because they can go back and they said we're going to go back, take this experience, in this hot, weather. We're going to be able to feed that forward into our next iteration of design. It worked perfectly in Hawaii when it was warm but not too hot. It had some problems in the really hot weather, and so at least in that case, the instrument scientists who are building it and designing it, they took that experience and they're feeding it forward into building a more robust, useful instrument in the future.
Yeah, challenge breeds innovation. We were coming up with some crazy, weird innovations for how to keep these things cool, like cooler insulation, and it was, yeah, we came up with some pretty creative ideas. And in that case, that's a good example because the manufacturers were actually out there and that's useful data for them. We wanted the data coming out of the instrument. They wanted the operational data. And that's what we're hoping to do with all of these instruments. I mean, at Goddard specifically, there's a group working on the next generation of in situ geochemical analysis capability. And what we're learning with the RISE survey team is feeding directly into that instrument development.
I hope that group is also looking at simplifying complex procedures.
Yep.
I'm serious. You get complex procedures in any kind of exploration environment, and you're going to run into problems.
Yep, and that's why it's been really great for us to have members of the astronaut office come out in the field with us because, we've had a couple in particular say, this is just not going to happen, right? And that's exactly the type of feedback we need and why it's really important for scientists to work with the human exploration community to understand what the actual constraints are. Because it's easy for us as scientists to say this should work, but if we don't work with the engineers and astronauts, at JSC, then we really aren't getting the right information.
Well, the engineers may make them more complex, so you got to watch that.
Any questions for anybody else in any of the other presenters?
Yeah, so this question was originally for Jacob and Kelsey, but I'd be happy to hear other perspectives and opinions too. But from your experiences, have you been able to identify any ways to incorporate autonomous or semi-autonomous robotics to support crew and productivity, whether it's for scientific exploration or maintenance purposes, things like that?
So we're
always looking at that as a potential option. And in fact, Desert Rats had some robots that were being operated telerobotically. Some of the rovers were actually driven telerobotically, both from the habitat and from Houston. The fully autonomous robot operations have not been something folks have jumped up and down about us doing. We'd probably love to play with it, but usually the things that we suggest the autonomous robots do are, it depends what you're testing. If you're testing the robot's functionality in an autonomous manner, the types of analogs that we run aren't necessarily what they want to be testing in. If you're testing the impact of autonomous operating robots that have already been demonstrated to operate well in the environments we're working in, then we could get into the operations testing a little bit. So I think with that community, we're closing in on that capability, but we're not quite hitting the same goals in a complementary manner just yet. But if you have an idea, we'd love to talk about it.
I have one over here. Okay.
Excuse me, could I make one comment on that? One thing to watch very carefully are these proposals for EVA crew to have robotic field assistants. We don't use them on Earth, we use graduate students. They're easier to direct. But more seriously, I think if you have a robotic field assistant, the crew's going to pick it up and put it where it wants it. It's just not something you're going to spend a lot of time directing. So in that sense, it feeds back into the kind of instruments that you would want to have and have available, is that there are instruments that if they take any time at all, you want to be able to set them or attach them to an outcrop or a boulder, and then walk away and come back and get the data later while you do other things.
Yvonne.
Okay, my question was for Jake, and I think I understood you to say that when you go through the lava tubes, you can actually take DNA measurements, and I was wondering if you've seen the DNA change with time or distance throughout the lava tube, and does it match the people that you took through there?
That's a really good question. So we started the DNA sequencing last year, so we haven't really looked at the longevity issue just yet, but that's certainly something we're interested in. We have detected changes in the tube with respect to distance from the skylight, and so the folks that do that work for us have shown some of that, and in fact there were some talks at LPSC on that topic specifically. So we do see differences throughout the tube, and in fact what's interesting is there are some differences between tubes that are not very far apart from each other. So within the field site, there are definitely uniquenesses. So that's something we're looking into more. And now, again, for each of the goals that we set for ourselves on the ground with instruments or science-wise, we then seek to integrate that into the high seas testing to draw the crew in trying to achieve those goals as well. So we're hoping to get more into that.
Clive.
Clive Neal, Notre Dame.
Thank you.
Yeah. I shouldn't introduce myself. That's question for David and Jack with regard to the pressurized versus unpressurized rover. David, you presented, I'd love to see that rover on the moon, as I'm sure you would. But given the architecture that we've been told about with the deep space habitat, there isn't going to be much of a way to get to the surface, let alone something that big. Is there a way around that? And Jack, your insight on the feasibility of using that pressurized rover in the way described is, based upon your experience, is that feasible? And I just like to get some input to the architecture and then the feasibility of getting that to the surface and using it.
Clive, so to answer the issue with the architecture, there is this design reference mission that was put together by ISEG participants, including a NASA representative. And so the question I think that they were trying to answer is, if we do have this gateway and we do have a capability of putting hardware and crew on the surface, what might we do? At the moment, the capability that nobody has designed or has stepped up to build is a lander, okay? So that's a missing element, and until that's resolved, you know, these are at some level paper studies, but yeah, you would need a capability not only to launch it, but I think that we'll have that with the SLS, but then to actually get those vehicles and crew to the surface. So I'm hoping that somebody will step up and say, well, let's build that lander. Jack?
I think that Dave made an excellent presentation on the capabilities, Clive, of a pressurized rover. I just would remind you that the discussions of keeping the suits outside the habitat or the rover or what have you began not too long after Apollo. And I think right here in Ames, as a matter of fact, with some of the early discussions. And the primary motivation there was to keep dust out of the cabin. Now, that has since, as Dave has so ably shown us, gone farther than that and shown that there can be efficiencies in utilizing that concept, efficiencies to exploration. I would worry a little bit about putting too much reliance on the comparison of times in 1 gravity and 1/6 gravity or 3/8 gravity, because they've invariably been wrong. The deployment of the ALSEP being a prime example. It always took, everything seems to take longer than you plan for. And it eats into other plans, of course. But overall, I think it's a great concept, and I would just caution you about worrying too much at this stage about architecture. I would try to establish options for the use of architectures, but until we have a clear statement on what the future of space exploration by the United States and its partners is going to be, I think it's mainly we're doing the right thing. We're trying to evaluate a variety of options that make sense. They're common sense options that would fit into several different architectures.
We,
Jack?
we need to be wrapping up here in a couple minutes for the next session, but is there?
Jack Lissauer, NASA Ames. This question is for Jack Schmidt. I'm wondering what access you had to samples brought back by previous missions before your mission, how it affected what you did when you were on your EVAs, and what your recommendations for laboratory work with samples for future EVA astronauts would be.
Wow. I had whatever access I had time to exercise. I spent quite a bit of time beginning with Apollo 11 on that. Some of you may have seen the so-called introduction to the first Apollo volume, and that includes a significant amount of observation of those samples. It really did, all of that really did help, because in one way it bounded the minerals I could expect to see, the textures I could expect to see in certain types of rocks. I don't think it inhibited my observations, but it certainly bounded some of them. And in fact, when I was on the surface looking at surfaces of various rocks, I could even see and identify minerals through the patina. But one thing I didn't expect to do is that I was going to use the effect of micro impacts to identify minerals. If a micro impact hit plagioclase, there was a white halo. If it hit something with a little bit of mafic material, it was either green or black. And so even that helped me identify minerals and distinguish between different rock types or percentages of minerals in those rock types. I think both for Mars and for future moon missions, you're going to, though, plan on doing a great deal of work, and maybe it's on alternating EVAs in the cabin on looking and getting more specific discriminating information about the samples, because there will have to, almost certainly will have to be some selection process in that, and the crew is going to be in the best position to do that with simple laboratory work in the cabin of the habitat, or potentially even in the rover, using some of the equipment that otherwise would be portable as well. Does that answer your question?
I'm sorry, but I think we are out of time. And the next session, I apologize, but please grab the presenter that you want to talk to, and the more questions you answer, the more questions you have. That's what happens. So let's thank our presenters one more time.